Are we ready to try something a little different? The next unit? Or the next topic, I should say? Okay. Well, this is going to be fun. Famous last words. We're going to do something that we don't typically do. In fact, in past classes, I've kind of skipped over this or minimized this section. But it really is interesting, and truth be told, we don't give enough practice to students when at analyzing and studying nonlinear systems in general. Maybe if you get into some advanced control classes, you'll develop some more nonlinear system theory. But this, we typically don't like to give you many tools for dealing with that because it's hard, and it taxes us professors almost as much as you students. But now we're going to figure out what happens when we terminate a transmission line with a nonlinear load. And in a way, it makes sense, right? Most of the really interesting stuff in our profession is nonlinear. Transistors are nonlinear. Diodes are nonlinear. Almost everything is actually nonlinear if you put a high enough voltage across it, right? So we want to be able to handle that scenario. If we've got a nonlinear device, like a transistor that could saturate, or a Zener diode, for example, how do we handle that scenario in a transmission line? So that's going to be the start of our next topic. Nonlinear loads on transmission lines. Okay, so here's the scenario we've got. This is what we know so far. I got a transmission line, the usual Z0 intrinsic impedance. It's terminated with a device. Let's just leave it as a mystery box, right? Mystery box. We're not going to say what it is yet. There's a voltage across that, V sub L. And there's a current that goes into there as well, I sub L. Out of the top bar into the bottom bar. Now, we also know that if you know what the load current is, and the load voltage, and the Z0, then you can calculate forwards and backwards propagating waveforms, right? Remember this equation, VL plus IL Z0 divided by 2 is my forward propagating wave. V minus is VL minus IL Z0 over 2. And in fact, if this is a purely resistive network, what we can actually do is substitute my VL is equal to IL times RL, Ohm's law, and then algebraically solve for V sub L and V plus. Or V plus with respect to VL. In fact, if I rearrange things around, what I would get is something in the form of VL is equal to some constant stuff times V plus, and that constant stuff will actually be my transmission coefficient. It's a simple double check. Now I'm going to show you how to solve this problem a slightly different way that doesn't involve algebra, and you're going to think, why are we going to all of this trouble? And then I'm going to put a device in there where there's almost no other way to solve it other than this technique. Something that does not have some simple algebraic V equals IR relationship with respect to it. So I'm going to presume we don't have this. And instead, I'm going to rearrange everything so that, let's see, I'm going to take the 2 over to here. I'm going to rearrange it so that I have IL expressed as a function of 2 over Z0 V plus. I'm taking the 2 here, putting it over here, dividing by the Z0 over here, and I'm subtracting VL over Z0 as well. Okay. So why did I rearrange it like that? And get ready for an example here. What I'm going to have I'm going to have IL, and I'm going to call this IL nu over on the left-hand side of the equation. 2Z0 times V plus minus 1 over Z0. And this voltage I can see as a function of IL. And I'm going to call that IL old. So for the case of a resistor, my function FIL, if that's equal to my load voltage, then I really just have sort of a constant RL times IL. This function is just a constant times whatever my argument is. I'm setting this up so that I can actually put an arbitrary function relating V to I into my system and actually solve it. Now, eventually you want to get this. This is an equation, and these are the same physical quantities. I sub L, old and new, those need to be equal. But you can't always solve things algebraically in these nonlinear systems. So what we're going to do instead is iterate. I'm going to first iterate with a resistive load, and then I'm going to put something a little more complicated in there and show you that it still converges and still does some of the same, has some of the same behavior. So how would we solve this system for a resistor using iteration? This will be nice because if I do it with a resistor first, I can at least double check my answer. Okay, so in this case I've got IL, and this is nu, 2 over Z0 V plus. My functional relationship is going to be IL old, RL over Z0. And I'm going to iterate this system until I get these two to agree. So my algorithm here is I make a guess, for IL, and call that IL old. And then I plug it into here. What is my forward propagating wave? That should be given at that point. I should be able to calculate what that is. Z0 is a parameter of the transmission line. RL is a function of what I've connected to it. I'll calculate that, and I'll get a new estimate for IL sub nu. That's my second step. Calculate IL sub nu from IL sub old. So I do that calculation. And then my third step, if my IL nu was not equal to IL old, what I plugged in to get that value, then I repeat with IL old now equal to my IL new value. And this is the iteration approach to solving complicated equations. In this case, a resistive example is not going to be very complicated, but it's going to be illustrative. And it's very simple. You say, what's the current probably going to be? You can pick whatever value you want. Pick 0. Pick 20 amps. Pick 1,000,000 amps. An educated guess always makes the solution converge a lot faster. So you might want to solve Ohm's law, or maybe make 0 because you know it's going to be a small value. You plug it in there. You calculate it. You find, oh, I didn't guess right because it says that my IL new, according to this equation, is 20 milliamps. That means I got to plug that guess into here and recalculate, and I get a new guess, and I recalculate. And what you should see, if the thing is set up properly, and I'll give you a caveat and a procedure in case it isn't. If the thing is set up properly, what you should find is that these values, after iterating several times, start to get closer and closer to one another. the delta increment between your new and your old becomes smaller and smaller. And in fact, computationally speaking, you're never going to get the exact same value in here. There's always going to be a little residual error. But that should asymptotically approach 0. And so it really becomes a question of, at what point do you consider success? Are you are they the same with respect to 4 significant digits, 5 significant digits, 7 significant digits? The nice thing about this is it's very easy to code up in a computer. So you have one of these examples on your next homework, and you might even want to write a simple 2 or 3 line program to iterate. And you'll have to have some sort of stopping criterion for that. 1 times 10 to the negative 5 amps or something like that. So keep that in mind. Let's work through this resistive example here, just to show that it does converge for that case. And the resistive example that we're going to have, I'll show you my circuit. I'm going to have 5 volts V plus and a Z naught of 200 ohms. Let's use a 200 ohm transmission line. A little bit non-standard. Getting tired of working all these 50 ohm problems. I got a 100 ohm resistor. This is my voltage across the load, and my current I sub L comes out and flows through this part of the circuit. Now, here's how I do my iteration. I'm going to put a guess, the iteration number. What I start out with, I sub L old, and then I sub L new that I calculate by iterating my equation. And of course, when I calculate that equation over there with these values, the equation that I'm iterating is actually I sub L new equal to 0.05 minus 1/2 I sub L old. And for my first guess, I'm going to guess 0 amps because I don't know what else to guess. And when I plug that in there, when that comes out as IL new is 0.5 amps. So I suddenly realize, I'm off by 0.5 amps. That's not even close. 0.05 amps, actually. And keep in mind, all the time I'm using the magic professor calculator where everything is calculated ahead of time. Mostly correct. So my second iteration, my I old becomes my I new. So I put in my guess of 0.05 amps. And out from this equation is 0.025 amps. So it appears that 0 has significantly undershot my actual answer because my IL new goes up to 50 milliamps. This next guess, however, seems to have undershot the answer because I go down to 0.025 amps. And so I keep repeating that. 0.025 amps. This becomes 0.0375 amps. And I plug in my fourth iteration, 0.0375 amps. And this comes out 0.03125 amps. And so forth and so forth. And finally, at iteration number 9, I find that I put in 0.033 amps, and out comes 0.033 amps. So up until at least 3 digits of precision, it's essentially the same value. Yeah?
I'm just wondering, why didn't you just initially solve and make them equal to each other?
Okay, so I said this is for illustrative purposes. We're going to do an example right after this where that's not possible. So, okay, let's take advantage of this. Now let's do what you said. If I plug this into one another, then I know that I've got V plus going down. Let's use some transmission line theory. I've got a load reflection coefficient, gamma sub L, of 100 minus 200 over 100 plus 200. That's negative 1/3, right? negative 1/3. So my transmission coefficient is actually going to be 2/3. Is that right? So I should basically get 10/3 of voltage across here. And that, when I divide by 100 ohms, should give me 0.033 amps. So you can see the long way wound up equaling to the short way in terms of our solution. Okay. Now let's solve a less trivial problem. And here's the thing. There are actually two ways we could set up these iteration problems. In the case of the simple resistor, this converged very nicely when I put it in as a function of I sub L. In some scenarios, when you start iterating, you're going to get a solution that diverges, like your I new gets farther and farther apart from your I old. And in that case, you've probably set it up in an unstable mode. And so the way to do that is, instead of solving in terms of new and old currents, a lot of times you can fix the problem by using this other formulation, which is just a rearranging and solving in terms of voltages. So let me put this equation up on the board, and then we'll work through the iteration here. So the other way to do this So we did it with the following formulation. IL nu is equal to 2 over Z naught, whatever impinges upon that terminal side, minus 1 over Z naught. And what I've got here is some function of IL old. If you want, you can rearrange it so that you iterate with respect to VL instead of IL. And in this case, VL new is going to be equal to, by rearranging this equation, 2V plus minus Z naught times the inverse, F minus 1, of VL old. And in this case, your functional dependence is the shape of your nonlinear device's VI curve. So if you graph VL and IL, in this case VL is equal to F IL. And presumably you have some weird nonlinear relationship coming through here that you could stick directly into this expression or invert it and stick it into there. In fact, sometimes you'll see VI curves drawn this way, right? Voltage will be here, and I will be here. In this case, it's IL is equal to the inverse of voltage using the conventions that I've graphed out here. What's a good example of a curve that you graph with a VI curve with those axes? What did you study in 3041? What kind of device did you study? Diode, that's right. What did a diode look like? That was a very nonlinear device. Kind of had a very small reverse saturation current, cross the VL equals 0, IL equals 0 point, and then rapidly exploded. Lots of current with respect to a little bit of voltage once you surpassed a certain threshold. Yes?
The functional dependence is the shape of the nonlinear what? I didn't catch what you said after.
I don't know. You're going to have to rewind on that one.
VI?
Yeah, so this is an example of a nonlinear VI curve. It's not a straight line, basically. A resistor would be, on this particular graph, would be a line whose slope was 1 over the resistance. That's what we mean by linear. Diodes and capacitors and inductors are also linear devices, and that's because the derivative or the integral that you relate voltage and current to are also linear operators. This is a memoryless device, but it's a highly nonlinear device in that there's no temporal relationship or time variation that you have to take into account. You don't have to take derivatives or anything like that. But the constitutive relationship between voltage and current across the terminals of the diode is highly nonlinear. And that, of course, is why it's interesting, right? You can do a lot of really neat things with that behavior that you can't do with simple straight lines. So, okay, let me work through another quick example. And this time we're going to look at a square law device. And that is a device that has the following constitutive relationship. Here's my symbol for a nonlinear resistor. VL is going to be equal to 50 IL squared. So my VI curve looks a little something like this. It's a parabola. Definitely not linear. And we'll use a standard value Z0 equals 50 ohms. The equation that I'm going to iterate, I'm going to do one now with respect to voltage. So copying down from here, I've got 2V plus over 50 ohms minus, actually I'm going to rearrange all this, VL old quantity squared divided by 50 ohms is equal to my VL new. And that's just rearranging that equation with the following constitutive relationship. Well, let me go ahead and iterate through the solution here. What's a good guess? Well, let me first give you a source side. We're going to assume that there's a match over here. To a 10-volt source. That I've switched it in at time equal to 0, like all of my other problems. I'm going to make that 50 ohms. So I send 5 volts down the line. I got 5 volts, voltage plus from top to bottom, going down to the end of the line. My V plus is going to be 5 volts. I got my 50 there. Well, I'm going to just guess a value. We'll see how good of a guesser I am. Iteration number, VL, 2.5 volts. I'm just going to guess 2.5 volts. It's half of the 5 volts that's striking the load. That's iteration number 1. I plug it into this equation. I calculate my V new. That becomes my next value for my load voltage. And it turns out it's smaller than I originally thought. It's 1.125 volts. I plug it in again, and I find my next value, 3, is 1.575 volts. Jumped up a little bit. And then 4, 1.420 volts. And so forth and so forth. And by the time I get to my 10th iteration, I won't exhaustively repeat this out. 10th iteration, my load voltage is 1.459 volts. And it doesn't change with respect to this last value. I have a convergence.
So basically, you can identify your stop point when you stop seeing any change in your value.
Exactly. That's how iteration works. You keep running it, and one of two things is going to happen. It's going to converge, and the answers aren't going to change anymore when you set up your equation. Or it's going to diverge, and you should solve it with respect to currents instead of voltages. You just rearrange the same equation, have it with respect to current instead of voltages. Yeah?
So you went about that iteration with those same steps?
That's right. That's right. Same steps. This was my new, I put it in there, and then it became, this was my old, I put it in there, this became my new value. Then I use that as my old value for the next iteration. And again and again and again comparing the two. I didn't feel like writing down both of the columns, because in some ways it's redundant information too, right? Whatever I put here winds up being the first thing over here and so forth. Yes?
So we could have done that iteration in terms of IL, if we were just solve for IL in the equation that you give us, the VO equals 50 IL squared, and then we could just use the IL equation and go through the same iterations.
You could have tried that. I believe for this particular example, if you iterate this with respect to IL, you'll actually get a divergence. Okay. So I picked the right one ahead of time.
Okay.
It'd be a good exercise when you go home in the privacy of your own home to code up the iteration with respect to IL, just to rearrange the equations and solve for IL news and olds. And what I think you'll find is that after about 10 or 20 steps, you'll start getting divergences on the order of 10 to the 20th or something like that. You know, it blows up. When it goes bad really fast, because it's actually exponential explosion, not exponential convergence. Yeah?
So does it ever happen if it diverges both in current and voltage?
That's a little trickier. There are actually some really nasty nonlinear equations where you could get both to happen, depending on what region of voltage and current that you're looking at. You won't see anything like that in this class. Let me just caution you ahead of time. But there are some instances, especially when if you have a nonlinear relationship, you can actually get multiple roots for I and L, VI and V and I. If you think you have like we'll talk about the tunnel diode when we come back. That'll be an interesting scenario to look at. That actually has a VI curve where the I actually, as a function of V, jumps up, then jumps back down, and then jumps back up again. So there's a region in space where it's not even invertible. You got to pick which solution you want. There aren't that many scenarios where that'll come up.
On a test, would you say identify with iterations from a range from 0 to 7?
Yeah, so this is always the quintessential question, right? How can I ask this on a test? It's fair, and you can do in 90 minutes, right? And so in that case, what would be fair game would be a simple nonlinear diagram, and I'd make sure that it converged pretty quickly. Or maybe I'd just say, write the first 3 iterations, output of the iterations, set this up. And I'd probably even be a softie and tell you which converged and which didn't. Okay, we're going to pick up on this topic at the end of next class period, or at the beginning of next class period, and do some interesting stuff with nonlinear circuits. So hold your questions until then. Okay. So before we get into the videos, I want to go to the board just very quickly and recount something that we talked about last time. I think I was kind of in a hurry, and we iterated a solution, for example, of a square law device. So you'll recall we had this device that had the following VI characteristic. Voltage at the load was equal to 50 IL squared. 50 IL squared. And one of the things that we said was you could iterate this with respect to voltages. And I put one of these equations up here. VL new is equal to 2V plus minus IL, or the VI curve evaluated for VL, old Z naught. VL new. And the whole purpose of iteration is you make your nonlinear equation out, and you basically iterate it, old, stick it in, calculate a new, stick it back in the old, calculate a new, stick it back in the old. And you keep doing that until they're the same value. And of course, one of two things is probably going to happen. There's actually more things that can happen. But these are the problems that you do in this class. There are only 2 things that can happen. One is going to blow up to infinity, and you're going to get a nonsensical answer. These are going to diverge. And the other one is that they can converge, and you'll get the same value. And when you keep getting the same value as you iterate, that's when you know it's time to stop. And I skipped a step on the thing because I was a little bit sneaky. If you ever get in a situation where something is not converging properly, then you can always switch your V old and your V new. What do I mean by that? Well, let's plug in some math here. So this was my IL, right? And in this case, for the square law device, IL was equal to the square root of VL over 50. I'm just inverting that constitutive relationship between I and L going through the nonlinear device. And yes?
Was it an inverse of the VLO?
What?
Was the function inverse?
Let's see.
VLO.
VLO.
Yeah, no.
Oh, it depends on how I defined it. But here, let's forget the functional dependence for a second. This was just an IL. I'm going to plug this into here. And this was basically the square root of VL old. So it depends on whether you put, so some devices it's easier to put the voltage on the abscissa and then the y-axis you put on the I, or vice versa. So I forget exactly how I defined it last class period, but this is effectively what we're doing. We're substituting the value for I sub L in there as a function of the voltage value. So this is my V old and my VL new, and I iterate that. Now I think if you did this for this example, this particular formulation would blow up. And so what we do is we kind of rearrange this, right? Let's take this and put it over here. Let's take this, put it under here. Let's square both sides. So I get VL old over 50 is equal to the quantity VL new squared over Z naught squared. Well, Z naught is 50, so that's 50 squared. I can cancel part of that with the 50 there. So this became 50. And what's more, I can iterate this equation now, and this time I'll do it in the opposite order. This is going to be new, and this is going to be old. So I've flipped it. And I missed this. I did not present this step, which I think was confusing in the last class period. So I apologize for that. I just started off iterating from here. I said, oh, yeah, you can use this voltage equation. And then I started iterating from here. And I never told you how I got from here to here. So in case there was any confusion, I just wanted to go over that. Remember, at the end of the day, if the thing converges, both of these are going to be the same value anyway. So I can flip old and new and just solve for a different form of the same equation if I get an instability. So, clear as mud? Any questions on that? My skipped step? Okay, good. Well, I wanted to show you a couple of plots from some transmission lines with nonlinear circuits. And this is not in your book. This is kind of fun. This is the kind of thing that professors put together as presentations so that they stay moderately sane. Okay. Here's all my chicken scratch notes if you want to review online what I presented. Oh, yes, Cameron.
What happened to Z naught?
What happened to Z naught? So Z naught in the example was 50 ohms. I just multiplied both sides by 50. There was a 50 squared here. There was a 50 here. There's only 50 left when I multiply through by that. Okay, so what kind of devices can we model now with our little nonlinear iteration trick? There's a lot of different kind of nonlinear devices. I think on your homework you have a diode problem, a VI curve of a diode that you need to iterate at the end of a transmission line. Here's a little brain teaser. I always like this little brain teaser. It is one of the problems in your book, I think. You got a DC source and a resistor, switched it in, and over here is this crazy op-amp circuit. And this is a really nice 3041 problem probably, or I don't know, what class do you study op-amps in? 3042, 3041. Probably, you see a couple times probably in some various classes. Well, you see, I got my negative feedback there, right? And you can use your assumptions for the op amp that there's no voltage drop here because it's got a negative feedback, no voltage drop, no current going into the op amp. This voltage will be whatever it takes to make this system work this way. When you calculate the Thevenin equivalent for this terminal, you get basically a single resistance value that is negative. Is that even legal? Well, of course it is. It's an active component. You got voltage power supplies here, so it can act like however it wants. You can often get transistors and biased semiconductor devices to act like an effective negative resistance. So here's a little brain teaser. What does that mean for the reflection coefficient at the end of the line? What'd you say? Can't change the signs.
Greater than -1.
Yes, greater than -1. The sign will change, and it'll be larger in magnitude than 1. In other words, if depending on the value that I choose, if I put a negative resistance on the end of here, I can get a larger waveform reflecting from that junction than is actually impinging upon it. Because you use the same formula, you get negative resistance minus Z0 over negative resistance plus Z0. In that case, the denominator is actually bigger than the numerator. You can get a magnitude reflection coefficient greater than 1. It's always kind of fun to play around with. Now, intrinsically, you can't do that forever with this circuit. Like, you could conceivably think of a circuit where you had a really bad mismatch up here, and you could actually build up an unstable, reflection goes down, gets bigger, comes back, reflects back, reflection gets bigger, comes back, gets back, and then the circuit blows itself up. But of course, we know that's not going to happen because this thing has a set of rails on it that are finite, right? You can only, if you looked at the VI curve of this device, this looks like a negative resistor up into a point. The slope of this, rise over run, current over voltage, will be 1 over that negative value that we calculated there, RL, 1 over RL, which is negative. I don't need to put a negative sign there. And then once it saturates, it'll kind of go back to having a positive resistance characteristics. So it's piecewise linear, but very, very nonlinear in its entirety. Very bizarre circuit element. And you could iterate this thing with this in the network as well. You'd have to come up with some weird piecewise functional linear dependence. But you could iterate this and solve this. Let me show you another nonlinear device. This is just sort of enrichment here. Does anybody know what has a curve like that? This is a VI curve with the point 00 put here. But it kind of goes like this, and down, and then back up again. This is a characteristic of a tunnel diode. Anybody studied a tunnel diode before? It's a really bizarre thing. It's also often called the Esaki diode, named after the Japanese researcher 50 years ago that invented it. It's not used too much, but one of the things, you make a tunnel diode by making an extremely thin p-n junction. And one of the nice things about that is that it operates at very high frequencies, at microwave frequencies, or higher even, millimeter waves. So you can use it in the gigahertz regime. And it has this peculiar hitch in its VI curve where it goes up and it comes back down. So if you biased it here, it would actually have an AC resistance that was negative. And you could conceivably get negative, greater than 1 reflection coefficients at certain points in time. Anyway, I have a little, I don't know if you can even see it, there's a little polynomial representation of this curve that I fit it to. I is equal to 150v to the cubed minus 120v squared plus 25v milliamps. Oh, yeah, Anya.
Can you give a short summary of what a diode is?
Of what a diode, okay. So a conventional diode is just, you take your semiconductor material, you dope a little bit of it at one junction P and a little bit at one junction N, And that creates a band gap that you can send charges across in one direction, but not necessarily the other. And then the VI curve usually follows something like this. And you've probably seen this in maybe your 3040 class. And so this, if you think about it in terms of slopes, the equivalent resistance of the diode is a function of where you've biased it. That's one of the really neat attributes of that you want to have. Over here, the slope is very shallow, nearly 0. 1 over the slope is the equivalent resistance. So this looks kind of like an open circuit back here. The resistance here is very steep, nearly infinity, which when you calculate the equivalent resistance, 1 over infinity is 0. So this almost looks like a short circuit. So really what you have here is a device that's a switch. This is a peculiar nonlinear version of a diode that has a really, really thin PN junction. And if you dope it at a certain thickness with some certain levels, you'll get this bizarre characteristic that comes out of it. So I just want to run through an example of something neat that you can do with transmission lines when a weird device is at the end of the line like this. I don't have my quantum mechanics notes in there, so I can't lecture about band gaps and things like that, even though that would be very useful. So here's the circuit we're going to look at. I got a voltage source, a little 2.2 voltage source, no big deal. It's nice because you don't need that much voltage to see kind of the goofy behavior. 0.2 corresponds to here on the diode curve. A source resistance, which I'm going to vary across the place. 50 ohm transmission line, because what else do we do in this class? Everything's 50 ohms. And then a tunnel diode at the end. And we're going to use that iteration technique. I'm going to do it on the computer. I'm not going to do it on the board, so that I do not belabor the point. And here's an example when R sub s is equal to 20. And you can see I can use the iteration. This is what computers are good for, right? Solving iterative equations and then doing it for each transit time. I believe my transit time in this circuit is about, I don't have it listed, but it's like 1 nanosecond. So I have a time scale here that goes from 0 to 50 nanoseconds. We see the first strike at the end of the line where the voltage kind of doubles up. That diode's kind of looking a little like an open circuit or a large impedance. Then there are reflections through the system, and then it shakes out to about 0.18, 0.17 volts in the steady state. So it's kind of doing exactly what a resistor is doing, except these are not going to be very regular reflections. But you get to a stable point. Any surprises there? Well, let me show you. This is kind of interesting. Let me show you what happens when you drop this to 10 ohms. Well, this is a very typical of nonlinear circuits. This is one of the reasons why many of our instructors, including myself, are scared to teach nonlinear circuits, because they do weird things. In fact, if you think about it, like I've been telling you these DC charging problems, I always say, oh, what happens when this is connected to a DC source for a long time? Well, here's an example of a nonlinear circuit that never reaches a steady state. It's oscillatory. Whereas the previous resistance, when I had 20 ohms of source resistance there, the wave would go down, bounce back and forth, and then damp to a single point. In this case, it's actually damping into a two-mode solution. It's now oscillating between 2 points, and it will do that forever. In fact, this is a very simple way to make an extraordinarily high-frequency oscillator. What's going to determine the frequency of this oscillator? Simple little circuit. Transmission line, source, tunnel diode. This is 1 nanosecond. It's, the transit time. What's going to determine the period of the oscillator? It's basically how long that transmission line is. So if you can control the geometry of your transmission line and you make it out of materials that don't have a big thermal expansion coefficient, you can very precisely tune your oscillator and it'll be stable. And it'll operate literally in the gigahertz or millimeter waves. But it violates everything that we've learned about these circuits in this class. There is no steady state, even though it's only connected to DC. And that's typical of nonlinear circuits. They do goofy things like convert frequency content in one part of your spectrum analyzer output to frequency content elsewhere. Linear circuits don't do that. Whatever frequencies you put into a linear circuit, those are the frequencies you get out. Not so with nonlinear circuits. Okay, just for the heck of it, let's put in a negative 10 source resistor. Is that legal? Yeah, we can build those. We'd have to use some active components like we did with that op amp. But we can do that. Yeah, do you have a question?
Yeah, for the last graph, and I guess for this one too.
Yeah.
What's the lowest that the amplitude will get to? Does it look like it was, like this one I can't really see it, but in the other graph it was decreasing. But you said it's never going to, like...
Yeah, so it turns out it's asymptotically, you'd have to take this out for a long way, but it's asymptotically producing a value that's going to be close to a little above like 0.21, 0.22 volts there. And then down here it's asymptotically approaching about negative or about positive 0.15 volts. But if you take this to infinity, it would hang at those values. They would never actually close. And then it's even more exaggerated here. This is a less stable circuit, because now we have this negative source resistance, which we can implement. And it's adding some additional energy to the circuit, and it's overdriving it. Now we're getting wild swings. Yeah?
What determines the high point and the low point?
Well, that's a tricky thing. You really have to do the simulations to get the high point and the low point. In fact, hold that question for a second because you'll see some interesting behavior. Now, what I'm going to show you, some of you may have seen in other forms. Let me just show you what happens if we lower the resistance a little bit more. Let's do negative 20. Huh. It still oscillates. So we get stable points. Emphasis on the word points. We've gone from 2 stable points to 4 stable points. It repeats itself at 4 different levels. Reflection, 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 reflection. And it falls into 4 stable points for all eternity unless you make a change to the circuit. If we go to negative 22 ohms as source reflectance, believe it or not, we now have 8 points. It will continue to do these 8 points indefinitely for all eternity unless we change the circuit. But look at what happens. You go reflection, 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 reflection. And it takes 8 times before I get back to the same point. Yes?
Why?
I'm getting to that. I'm getting to that. This is actually very characteristic of all nonlinear equations, all nonlinear systems. Whether it's a drippy faucet. You ever listen to a drippy faucet? Sometimes it goes plop, 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 plop. Other times it'll go plop, 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 plop. And then there are actually 4 beat periods. And then there's a point where it just starts sputtering all over the place. And that's what happens when we go to negative 25 resistance. The system becomes chaotic. It will never repeat itself. But it's stable. It's bounded between values, and it doesn't go off to infinity.
More for
Yes?
Even though it's not reaching the steady state, as you said, it's also have a pattern.
That's right.
Is it kind of like an implicit steady state?
Well, let me show you a different graph where I've swept the resistor values and shown the output. Please hold your questions. So what I've done here is I've swept the resistance values, and here's actually the reflection coefficient on the source side. And here's the collection of output amplitudes of voltage I get from my circuit. Here's the part where I had a low positive resistance, and I was just getting one steady state. And as I lowered the resistance value to like 5 ohms in it, this is called a bifurcation. And that means that now there are 2 stable points that it oscillates between. And then as you keep going down, there's another point where it bifurcates again, and again, and again and again and again and again. And finally, there's a wall, a geometrical limit that you approach, where the system becomes chaotic and it basically does not repeat itself. This is actually a really interesting circuit. There are lots of chaotic circuits out there, and they're very interesting in the fields of cryptography, of authentication, and identification, of random number generation, because they exhibit something called the sensitive dependence on initial conditions. In other words, this solution will jump around in this region. If I pick a value and just stick with it, it will jump around and never repeat itself. I can try to simulate that on like a SPICE program, but it turns out that unless I get like infinite precision, it doesn't take long for the real world output and the SPICE program output to diverge and then completely disagree with one another. Very interesting property. The other thing to notice here, too, is that within the chaotic region, you have these islands of stability, where the system slips back into stable modes. And they're usually odd stable modes. Here's one that happens 3. Like if you're hanging on this one reflection coefficient value, you will jump between 3 stable points. If you move a little bit to the right, you'll go back into the chaotic region. If you move a little bit to the left, you'll start the period doubling thing, and then you'll get back into the chaotic region, where you go from 6 stable solutions to 12, to 24. So it's interesting. How many of you have ever seen a chaotic system before, or a plot like this before? Anyone? This is like a trendy thing to study for mathematicians in the 80s and early 90s. They're kind of interesting. But there's one really weird thing about this. Remember we talked about the drip of the faucet? So I've got the bifurcation intervals here. Here's the first bifurcation as a function of reflection coefficient. Here's the second interval. Yeah, it's a good bit shorter. The third. And you could draw, I don't have the resolution to draw it on the screen, but you could draw the fourth, the fifth, the sixth, the seventh, the eighth. All nonlinear systems behave in a very similar fashion when they slip into the chaotic region. The dripping faucet, a water wheel with leaky buckets, all of these things. And the really interesting thing is the ratio of this interval to this interval to this interval, as you get closer and closer in the limit, it always approaches, for any nonlinear system, the exact same number. 4.669201692. That's a fundamental mathematical constant. It's called Feigenbaum's constant. All systems do that, no matter what parameter you plot them against. Isn't that weird? The drippy faucet, the leaky water wheel, the chaotic circuit. Those things don't have anything in common other than the fact that they're third-order differential systems. It's enough to make you go crazy. So this is an example of a chaotic electrical system. There are chaotic mechanical systems. And you always need the same ingredients in electrical systems. There was a professor out of Berkeley named Leon Chua who came up with these Chua circuits. He was really the first one to show chaotic behavior in electrical systems. And he showed that the minimum ingredients, you need at least 5 elements to make a chaotic circuit. You got to have at least 3 inductors or capacitors, because chaotic behavior doesn't show up unless you have a third-order system or higher. So a little RC circuit, can't do it. RLC circuit, you can't do it. But what is the order of the differential equation governing an electrical system related to? Yeah. Number of inductors and capacitors, unless they're connected in a trivial manner. It's basically the order in your system. So you need to have at least order 3 systems, because you have to have a system that has at least 3 dimensions of phase space in order to allow for this, what's called a strange attractor, to define the solution space. You need that. You need a little bit of damping, so you got to put a resistor in there, and you need some sort of nonlinear element, and one that has negative resistance in it, or a source, or something to give energy to the system. Because if you don't have energy, No matter how crazy your circuit is, it's going to decay to a zero state or some trivial state. It needs a little driving the solution. So Chua's circuit doesn't involve a transmission line. It involves those 5 components: 3 capacitors and inductors, a resistor, and then something called a Chua diode, which is just one of those piecewise nonlinear devices. And you can build it very easily out of components that you find at Radio Shack. Now I have a question for you. We need at least a third order system to see chaos in a circuit. And yet this one, we have our nonlinear element, we got the tunnel diode, we have a source supplying some force. There are no inductors and capacitors in there. I just have a transmission line. How did I get to order 3 circuit behavior or higher?
The transmission line is made of inductors and capacitors.
Yeah, that's right. We smuggled them in the transmission line. Remember what the transmission line is. It's an infinite number of intertwined capacitors and inductors. It has infinite order, depending on what time scale you look at it. So that's how we were able to do it. Okay, so if you want to read a little bit more about these systems, here's some references. They'll be on the website. And I have a challenge. I thought of a good challenge for the class, in case you've got, like, you're Georgia Tech students, so I know you got loads of spare time. And if somebody wants to build and demonstrate a transmission line circuit that exhibits chaotic behavior, I'll give you extra points on the final at the end of the term. If you can demonstrate it to the class before the last day of class, you just need to build a chaotic circuit with a transmission line in it, and not a chaotic circuit that I connected a transmission line to, something that actually uses the transmission line. And we'll say like 10 extra points on the final. You can work in pairs of 2 or 3, but then you got to divide the points between the team members. So I thought that might be fun. I don't know if we'll have any takers, but it'll be a fun little hobby project if you want to get into it. Any questions? Now's your time to ask a question.
Like, I understand what it's modeling, but like, why would you make it intentionally? Like, where can you use this?
Where could you use something like this? Well, it depends. It depends on which region that you're operating in. So a lot of the logic circuits that we study in class are going to be operating over here, where you got one stable point, and it's important to be able to do iteration to find that stable point, because that'll basically determine the quiescent point of your circuit. This is kind of an interesting region because you can build oscillators in there very simply. And as we said, transmission lines that are short have transit times on the order of picoseconds, which means if you make an oscillator out of them, you have an oscillator that has frequencies of tens of gigahertz. You can get up in the millimeter wave frequency if that diode has enough characteristic to it. And these are kind of interesting over here because, as I said, you can use them to make things like random number generators that are very unpredictable. You can use them to do authentication, to figure out exactly what the reflection coefficient is, and then produce an output that has a very unique signature to do it. Exchange that as a key between 2 users in a cryptographic code. Those are some examples. And it's just fun. And it's pretty. That's the other reason.
It's supposed to be symmetric. So
what is supposed to be symmetric?
Like the way it's, because it kind of looks like 2 bells and then like another 2 bells.
Yeah.
Another 2 bells.
There is a crude symmetry to it, but it's not exact at all. Yeah.
Hey, so what is that 4.669 number again?
That is a Feigenbaum's constant. That's the ratio of this interval to this interval, or this interval to this interval. And it becomes exact as you approach the wall of chaos as a function of whatever parameter space that you're looking at. So anybody read a book on chaos theory? No?
This weekend.
There's actually a really good book that was popular at the end of the 80s called just Chaos by James Gleick. He wrote a really nice biography about Feynman, too. They were very interesting books. He's a good writer, and it's not too technical. So But an engineer will have no problem plowing through that book. It's a good introduction. But he talks about all the systems that kind of behave in this manner. Anybody seen a copy of a picture of the Mandelbrot set? It's a kind of a bizarre-looking fractal geometry construct. It kind of looks like this, and it's got all these like reservoirs off of it and circles. Does anybody know what I'm talking about? I can't draw it. It's too complicated. So it turns out that the ratio of the diameters of these circles also follows Feigenbaum's number. Yeah, it's a simple iterative procedure where you square a complex number on the complex plane, add 1, square it, add 1, square it, add 1. You repeat that to infinity. If it diverges and becomes infinite, it's outside of the Mandelbrot set. If it converges or oscillates, it's inside the Mandelbrot set. And it turns out to exhibit this exact kind of iterative behavior. Purely mathematical attribute of nonlinear systems.
When was the constant derived? Like, in what year?
In the 70s, there was a man named Mitchell Feigenbaum, who's a mathematician, and he was studying these systems, and he had an HP calculator, which back then cost hundreds of dollars. And he was able to sit there and calculate it to about 3 or 4 different digits of precision. And it probably wasn't until recently that we could calculate it to that precision.
So you're almost saying that chaos isn't chaos?
Yeah, it's really not named properly. There are, even when it's chaotic, there are certain patterns and structures within it. But interesting branch of mathematics. Probably falls more in the systems and controls area of our profession. But it's nice to know you can show it up make it show up in an electromagnetic system. Okay, enough fun stuff.